where it sits on that graph? Okay, Emily, give me some words.
Where it sits there on the graph because, well, it's at 0.01% and it's under the 95%.
I love it. It sounds like, I want to show you guys something. You can vote if you like it or not. Here is the actual statement of what you're looking at. Natasha, please, go.
I was just
No.
making hand motions.
Oh, okay. The hand
I was
motion's fine. I like
I was
hand
moving
motions.
the decimal.
Oh, good for you. So it's point, good,
Yeah.
good. So 0.1%. Good for you. Good for you. 1 in 1,000, yes?
Yeah.
0.1%. So this is the mathematical conditional probability. We went into the study assuming that green tea was going to have no effect whatsoever on lowering breast cancer. And then what happened?
It was true.
We got data that disagreed with that. The idea is, did your data agree or disagree with this? Well, we went into the study assuming that it wasn't going to do anything. And what the hell did it do?
Nothing.
It looks like it lowered it, right? It looks like it lowered it. That's why it ended down here. If it did nothing, Natasha, thank you for that. Thank you for asking that, or saying that.
Yeah.
If green tea from our study looked like it did nothing, where would it have landed? It would have landed basically somewhere in here. These are the usual breast cancer rates right here.
Okay.
If green tea didn't do anything, it should have landed right there. If it landed over here, we'd go, oh, it's doing something, the wrong thing. But basically, if we didn't think, good for you, if we didn't think that green tea was doing anything to lower breast cancer rates, and we got back data that said green tea's not doing anything, it would have landed in here. Melanie, please.
Has this been replicated?
That's a good question. I'm not sure. I haven't checked it myself. I know green tea studies have been replicated. Whether or not the process of this particular experiment has, I can't say. Melanie brings up a good point here. Studies that are replicated are very, very important, but you have to replicate the study exactly in order to say it's been replicated. You can't just go back in and say, okay, we checked green tea in this particular province, blah, 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 with different control groups. It has replicated exactly the same way. I don't know. That's a very, very good question. I get too busy tracking other studies, and I lose track of the ones I've already done. Thank you. That's good research, though.
Well, how would you know if it's an outlier? It's a pretty significantly lower.
I'm not saying it's not. It is significantly lower, which makes me believe their conclusion that there is an association. Until it's been replicated, though, we can't really eradicate Linda's doubt about whether it was an outlier or not. Every data set's going to have extreme outliers. Now, the thing is, are we expecting to see it on the first try? That's what's making you guys kind of scratch your heads. Every data set is going to have every large data set has extreme outliers. But are we going to draw it on the first go? Probably not, yes? Remember how upset you guys with 5 black cards?
Yeah.
5 black cards, first 5 pulls, 5 black cards, and I said, what the hell? It could happen. You're like, yeah, but in the first 5? This is the first 5, yes? This is getting the first 5 black cards. Now there's 2 explanations. One of which, as McKenna just pointed out, is that your deck is rigged, rule! That's one explanation. Deck is rigged, which means we've got another deck's curve over here. The other explanation is what Melanie just hinted at, is that it is indeed an outlier. We never know if it is or not. It's pretty extreme, like you said. I want to offer a caution about that too, if it's okay. That's a pretty small p-value. I mean, by any standards, 1 in 1,000 is a very small probability. I've seen certain studies weight p-values as meaningful. In other words, if another study came back at 0.005, they would say that this one is 5 times as extreme. You can't do that because essentially what you're doing then is you're ignoring the margin of error around your data. More on that soon. But I agree with you, that is a small. Perfect implication would be a way to see if it's actually metriced as an outlier or more likely a new curve. It's not a very satisfying answer, I know. But that's the only way to do it, is to replicate the study again, which is why many studies aren't replicated properly. It's too much work. Yes. Please, Veronica.
Well, I was just confused because you said that we could have a separate curve, but this is just the third possibility, is that it's lowering the rate of cancer. So there are the 2 possibilities of outlier or it being on a separate curve, or it could
Do you
prove
see how the second 2 things you said are the same thing? There are only 2 possibilities. One is that it's an outlier. I'm not doubting that it could be an outlier and we could just be getting fluke results. And if it gets replicated, we come back and go, dude, green tea didn't do anything. You just got goofy data. The second thing you said, that it's on a separate curve, and the third thing that you said is that green tea is lowering breast cancer, those are the same thing. Because what does the separate curve mean? That green tea drinkers have a lower average breast cancer rate. In other words, there is the number 2 and number 3 are the same thing.
Oh, okay.
The separate curve means there's some other breast cancer rate significantly lower than the non-green tea drinkers.
Okay.
You see? So make it even simpler for yourself. Either it's an outlier on this curve, or it's a normal occurrence on this curve. Is that fair?
Yeah.
Good.
I just didn't understand
Hey,
that.
that's why we're doing this.
Because I thought when you said there was a separate curve and that dot falls to the right that we're seeing increase.
Okay, so my point, and again, thank you, Veronica, for this statement. Because I slapped this curve over here. I was kind of cavalier with where I put it, because I don't know where its exact center is. The whole reason you're doing these studies is to trying to see if there is a reduced breast cancer rate. So I put it kind of over here. Why didn't I put it further to this side? Why didn't I have this more on this side? I don't know. I don't know, because I was just trying to show a curve that this more likely looks like it lives on. Do you see how this asterisk looks like it's more at home on this orange curve than it is on this gray curve? That's the point. Don't think too mathematically yet about it. We'll get to the mathematics on Thursday.
I missed the overarching that the green tea drinker breast cancer is lower on the number line.
And that's why we're taking the time and spending 2 days doing this, because I want you to get the big picture before we start micromanaging this. Natasha, go!
Okay, so how does that prove anything though? Because there's like a 50-50 chance that there's a curve or an outlier, right?
No, it's not 50-50.
It's not 50.
But first of all, I want to go back to your first thing. We're not proving anything. We're looking for associations that can then hopefully be replicated if they show interesting results.
Okay.
So please,
Don't.
that's not as impressive as saying, I just proved you should all go get Arizona iced tea and drink it. I'm not.
Yeah,
We can say that.
The sugar might cancel.
The sugar might kill you, but the green tea is going to lower your breast cancer rate, while we simultaneously give you type 2 diabetes. No, I'm not saying we're proving anything.
Okay. You're just trying to find
And I love what you said, 50-50. I love that. That's like saying, if I may, paraphrase, when I step into the crosswalk at COCC, there's a 50-50 chance I'm going to get killed by a passing motorist. Why? No, think about it. There are 2 outcomes. I either do or I
That's
don't.
not how it works.
It's not 50-50. It's binomial, but it's not 50-50.
Yeah.
Thank you for that statement. It ties into what Linda said. It's not 50-50, but it is binomial. It's either on this curve or it's on this curve, some other curve.
We don't know the performance.
Correct.
Okay.
So what you do is you say there's a very, very tiny chance it's on this curve. What's the chance it's on that curve? You saw it in the article.
Okay, so there's a smaller chance it's an outlier.
Boom!
Okay.
Yes, that's what you're measuring. You're saying if that chance comes back teeny tiny, teeny tiny, teeny tiny, teeny tiny, there's a very, very tiny chance it is actually on the null curve, which means there's a better chance, most likely it's on some other curve.
Okay.
Thank you for that. Thank you for comparing it to a binomial, because essentially it is. Either, it's binomial in this respect. Either this is true, or this is true. But it's not a coin flip. If it was a coin flip, every statistical study would be done with a quarter. And we'd save a lot of money doing results, and we'd have lawsuits out the wazoo, which we needed, because we save all the money from doing the results with coin flips, we have to pay out the lawyers. It's not coin flips. The coin flip is the data analysis, which we will get to. And the point is getting that p-value. If you get a teeny tiny p-value, it's very hard to believe this. Because it's very hard to believe you're on this curve. This curve is this belief.
Gotcha.
So the smaller your p-value is, the more likely it's just a different.
It's on. Yes, thank you. Thank you. Say that nice and loud again, Tasha.
The smaller your p-value is, the more likely it is that's on a different curve.
I love that. If you can put that in the back of your mind for the rest of the day, the rest of the day is going to go smoothly. The rest of the course is going to go smoothly. Smaller the p-value. Can I say it a different way? The smaller the p-value, the less likely it's on the null curve. Can I say it that way instead? That's actually more mathematically correct than saying it's more likely on some other curve, because what you're doing is you're going in knowing the center of this gray curve. With a small p-value, it's hard to believe it's on this curve. So it's, you know what it's called? The old school language, when you get a small p-value, is you reject the null hypothesis, which means you can't believe this. So by rejecting this, you kind of by default have to accept this, because that's the complementary advice. It's a complementary statement. Thank you for comparing it to a binomial. It was beautiful, beautiful comparing to a binomial. Just not 50-50. Yes, that's the important thing. Yes, I'm seeing lots of yawns. Let's take 5. Lots of yawns. This is heady stuff. Heady stuff for no mathematics going on whatsoever. Yes.
Yeah.
Great questions. Thank you.